Okay, so this is the Deep Vision session. If you're not here for Deep Vision, go to the other room. They said that on an airplane once. We're going to Los Angeles. If this isn't your plane, two people got up and walked off the plane. So my name is Gershon Panich. And just by way of brief personal introduction, I wear a number of different hats. On the academic side, I teach patent strategy in the MBA program at Tel Aviv University. And I'll make a quick push for my class. If you take my class, you'll learn that it's really easy to get a patent, but very, very, very difficult to get a patent that actually creates commercial value for your company, that blocks your competitors. And patent strategy, what we teach in the class, is how to get there and how to do that. And on the non-academic side, I practice what I teach and work with some of the largest and most interesting machine vision companies here in Israel, including maybe one that you heard about in the press very recently, and many small ones that you haven't heard of yet, but you will. When the organizers asked me to chair this, they said, you know, you don't need to tell this crowd about deep vision because that's why they're here. They're the experts, so don't tell them about that, but show them some statistics. So I started to look for statistics, and there's really no statistics in deep vision. But what I'm learning is that, and what you already know, is that in the field of artificial intelligence, deep vision and neural networks are really in a very exciting area right now, and deep learning is really driving most of the artificial intelligence companies today. And so if we can put up my first slide, I found some statistics for you. This just shows you sort of what's happened just in the last few years. I mean, in 2014, 2012, when Face was acquired by Facebook, they were one of the first. And now look at all the activity that's happening and the major companies that are buying deep learning companies. If we can go to the next slide, you can see just in terms of the number of mergers and acquisitions that have happened just in the last few years. By quarter, we're really on a significant rise. So if you're working in this field, as you already know, you have an incredibly bright future. Okay, so let's talk a bit about what you're going to hear today. We're going to hear from three very exciting companies that are all doing deep vision in one way or another. The first company is Visualead. You may recall Visualead from IMVC back in 2014 when they won second place in the startup competition. Shortly after that, Alibaba made a strategic investment in the company. Their technology that they presented at the time had to do with making your QR codes look pretty. And so they were able to blend into a QR code some kind of a visual representation. They've, I wouldn't say pivoted, but they're moving in a different direction now that's very interesting, and they're going to talk to you about that today. And that is creating 3D or virtual 3D images from video and extracting the background in a video and being able to sort of simulate a 3D image from video. So speaking to us about that today are Gilad, Sharir, and Eddie Smolyansky. Gilad is Visualead's senior computer vision researcher, and he applies deep learning research on innovative scenarios. And Eddie is the head of research at Visualead and is responsible for the company's innovation and next generation of disruptive technologies. So without further ado, Gilad and Eddie, please take the podium.
Hi, everybody. Yes? Thank you, Mr. Gerson, for introducing us. It's a pleasure to be here today. We have a long history in IMVC. Every year so far has been a step up, so by extrapolation, I guess next year we'll be the keynote speakers. So today we'll tell you about our work in creating spatiotemporal representations for video and doing object extraction on them. We'll start by describing our mission and challenges, which is basically what we do and why. Then we'll go over our method for creating a spatiotemporal representation out of a video, which prepares us for the next step, which is object segmentation. For this, my esteemed colleague Gilad will come to the stage and tell you about our deep learning technology for segmenting any object in a video. Throughout the demonstration, we'll show you some results, and we should have enough time for a live demo at the end. So, in Visualead, our vision is to connect the physical and digital worlds. So to this end, we're making a product which enables you to capture, with any smartphone, to capture an object that you have, and like this, right? And get a spatiotemporal representation of it, which you can interact with and embed in different environments. So there are many use cases for this technology. For us, due to a long-standing partnership with Alibaba, the natural place to start is e-commerce. Imagine buying a product, and instead of seeing just two stills images, you actually get to rotate the product or even peek inside of it. Finally, remember, we're capturing video, so basically we're moving on a fixed track in space. But if you do it in the right way, then you can create a 3D experience and give 360-degree information. Now, one thing that really helps to sell this 3D feeling is video segmentation. So, for example, if you look at this minion, it looks and feels 3D to you, but actually it's just a bunch of two-dimensional frames. And now that we have this minion segmented, we can put it in other environments. So I think the best way to explain what we're doing and our challenges is to start with an example. So we have this original video of a girl in Habima Square, taken by an iPhone 6, handheld. You see people going behind her. And our first challenge is to make the file size much, much smaller, because if you want to do something at scale, and in our case we're working in Alibaba scale, you can't have 30 megabyte videos, which is what this is. You need to have a factor of 15 less. So the first thing we try to do is just do naive compression, and by that I mean we took 1 in every 10 frames. It's like severe decimation. And this is what you have. Now you see this is shaky, the panning is not smooth, and many of the frames, if I were to stop in the middle here, many of the frames are flow quality. They're blurry or otherwise something's wrong with them. Now, I'm going to show you something that's exactly the same file size, right? But after we've done some processing to it. We call it smart frame selection and stabilization. And you can see the differences. Now that it's good, we have something we can work with for the 3D experience. And as a teaser to what's to come, we take this girl and we do object extraction on her. And you can see that the color represents the foreground and the grayed out area represents the background. So how do we do this smart frame selection? Imagine these are our frames, right? And we want to take the best ones. So we were inspired by a Microsoft paper called Hyperlapse from 2015. It's a really good one, which tackled a similar problem, but in a different domain. They wanted to take very long videos of activities outdoors, for example, and make them, for example, 10 minutes long. So what you do is for each frame, you calculate a score by itself, which explains its quality. It can be blur or luminosity or other things like that, and it's in relation to its neighborhood. And also, for each frame, you look at the possible frames it can jump to, and you make scores for every pair, right? And that score can combine things like the smooth camera pan term that we want, and stabilization. And the way it works is you just calculate transformation between the frames, and you look for transformations that allow you to maximize your terms. Finally, we even look backwards to previous frames, and we calculate acceleration, which means we want the skips for the previous frame to this frame and the skip from this frame to the next frame to be similar. When you add all these terms up, you get a cost matrix where each cell represents a jump from frame I to frame J, the cost to do it. And now we want to do a global optimization to find the path of least cost across all the frames and get the best frame selected. So if we look at a zoom in of this, you can see a naive selection, this white line, would go to areas which are red, for example, here and here, which means the cost there was very high. While our optimization goes to good areas where you have blue and green. The way we do it is by a sort of dynamic programming, but we also have triplets of frames, so we need to do like an additional dimension of optimization on the dynamic programming. So this is our result for now. We have the frame selected, and it's ready for stabilization. We already have some stabilization from the previous stage without actually deforming the frames at all, and now we do more standard video stabilization. One thing to note is that we're only finding the transformations on the object itself. So we track the feature points on the object. You can see it starts on her shirt and it goes all over to her face, but there's never new points on the background. So even when she turns and new points appear, they're only added to the consensus set if they fit the object. To summarize, let's look at another example. Here's a video. It's even less stable than the one before because it's taken with an Android, no internal stabilization. The naive compression would look like this. And this is about 15 times smaller, but it's horrible. It can't work with it. After we did our optimizations on it, this is how it looks. And finally, and this is what Gilad will explain right now, we're doing object extraction, which gives you this effect. Gilad?
Fantastic.
Yeah. Thank you for the first part of the lecture. Now I'll go deeper into the object extraction part, and I hope you find it interesting. So our problem of the general object extraction is related to semantic segmentation. And you can see in this diagram an explanation of this problem where an input image, the model is trying to predict for each pixel the most probable class label in this example. So our problem is related to that, where we're trying for each pixel to predict whether it's foreground or background. And in our case, the input data is our videos. So the problem is even more complicated because we need to solve this optimization problem for each pixel in each frame of the video. Even though the object changes throughout the video and the background changes as well. The problem definition is semi-supervised, which means that we're given as input one frame which is segmented by a user. So we can use this ground truth label for one frame to segment the rest of the frames of the video. To give you a preview of our results before I go deeper into the technicalities, you can see in the upper video the input to our system, where the object deforms a lot and the background changes. And our result is almost a pixel-perfect segmentation of the input video. So how do we achieve this? We tried using convolutional neural networks. We tried various architectures, and I'll present a simplified version of our model. In this slide, you can see in the graph here the simplified version, which looks complicated but can be broken down into several components. which I'll explain in the following. First of all, we have our basic architecture, which we're based on, which is the Vgg network, turned into a fully convolutional network. Then the other components are the loss functions, which we modified, skip connections, and additional data of optical flow, which I'll elaborate in the following slides. So the Vgg network is a very popular model composed of simple parts, which are 3x3 convolutions. And the standard model is just predicts one class for the whole image. In this case, it predicted inaccurately that it's a cat. But if we want to get a prediction for each pixel in the image, what you would normally do is replace the fully connected layers at the end with a convolutional layer, and then resize your output image to the size of the original input image and compare it to the ground truth. And by computing a loss function on this on the ground truth and input and prediction of the network, you would backpropagate and train your network. In this case, we changed the normal loss function with an additional IOU loss function, intersection over union loss, which I'll explain. The intersection over union loss basically tells you how much your prediction intersects with the ground truth over the union of the positive prediction and the ground truth. It's described in these formulas, and also you would need to compute the derivative of this loss function in order to do the backpropagation. An additional component of our network is the skip connections. The skip connections allow you to combine information, the data from different layers of the network. The problem with the last output of the network in C5 is that it's very low resolution, even though it captures the general form of the object. So if you would want a higher resolution result, you would need to fuse together the higher details from the lower part of the network with the rest of together with the end of the network, and compare the fuse result with your ground truth. You can see a visualization of the intermediate results in these images, where you can see that in the earlier stages of the network you have more detail but less definition of the central object, where the fuse result has the advantages of both all of the stages of the network and has more details. The last component that I'll discuss is optical flow, which is a key feature of videos that, in addition to the regular frames, you can also use the data of the object motion. We found that this sometimes helps us separate a moving object from the background. So we compute the motion using optical flow. The method that we chose was Epic Flow, which is one of the state-of-the-art methods for computing optical flow. And in some cases where the object moves, this allows us to, this helps the model separate the object from the background. And how do we use optical flow? We train two separate networks, which are symmetric. One is trained on the RGB input images, and the other network is trained on the optical flow images. The intermediate outputs from each layer is combined with the fuse layer and compared to the ground truth. And in this way, the network is able to, by training the fuse layer, it's able to choose whether to use more of the optical flow or more RGB input. Finally, after we defined our network architecture, where The next question is how to train our network. So we employ a technique called transfer learning, which basically is a common technique that you start from a pre-trained network architecture. In this case, trained on ImageNet, which trains the features of the network to recognize object categories. And we fine-tune it on a separate data set, which is a data set of segmented videos. This allows the network to recognize and segment general objects in the video. And now, since we have a ground truth label for each video, we can further optimize our network for recognizing a specific object, which is presented in our input video, by training on a single frame of the ground truth that we're given. In this slide, you can see a few results with different parts of our network, and the basic thing to note here is that most of the improvement in accuracy is a result of the transfer learning between the original network and the parent network, and training on our specific video input. Here is another result where you can see the network was able to segment the object almost perfectly. And finally, leave the stage for my colleague to show a live demo.
Second. So, So we had a live demonstration, but we're having some technical difficulties with connecting the phone and the computer. You can come see it later. We'll be right here. We'll show you how it looks when, like what I did while Gilad was speaking, I took a video of this cute little minion on the floor, and we have it rotating and being well segmented. And also we have many other objects that we wanted to show you, so come over later. We're almost out of time, so let's do a conclusion. We spoke to you today about two parts of our work. One where we did spatiotemporal representation for a video with dynamic programming and finding cost matrix and then doing stabilization. The other where we do video segmentation. And what we learned is we don't know what will happen in the future. Like maybe in 5 years, everything will be solved with machine learning and AI. But today, there is still space to have both skill sets of more traditional algorithms and deep learning. And it's good to have both. The other thing, if you take one thing, the one thing that we'd like you to take home is that you need to trust your nets when you build them, because like what we talked about today, the different building blocks, is all very good, but we didn't tell you about all the failed experiments, and there are many. And most of the time it happened when we tried to force the network into some different configuration or add layers in places where we thought they would help. But actually, most of the time, just keep it simple. Let the net optimize. It knows its job better than we do. The exception to this is when you add new information to the network, either from within or from without. So, example for this is when we did the skip connections, we took the high resolution information from the lower, shallower layers, and we brought it to the end because it was lost in all the pooling. Another example is how we use the transfer learning to learn from ImageNet and then from the Davis data set and finally online from the one image. And for our future research, we think about ways to get even more data. We can think about maybe temporal connections between the frames, which is more than motion, or how to get data in other ways. Finally, in about 2 months, there's going to be an international competition by the same guys that made Davis. It's called the Davis Challenge. And we plan to be there and compete for first place. So we'll see you there, I guess.
Are there any questions? We'll take 1 or 2 questions.
Okay. Yes.
Speak up if you can. Yeah.
So I have a question about the first part, specifically the stabilization. You had to initialize the stabilization in some way. So why didn't you use the object segmentation stabilization?
Can you say again, please?
Why didn't you use the object segmentation part at the stabilization to initialize the stabilization part?
So we could actually, that's a really good question. We could have used the segmentation before the stabilization, and it actually would have helped us because when you get segmented object, you already know which feature points you want to track later. But you also saw in our deep net that we're using optical flow. So by doing the stabilization beforehand, we get much better information from the optical flow. But you can also say that now that we have a segmented object, we can do a second round of stabilization, which should be more accurate and better. So that's a really good idea that we'll explore.
Thank you.
All right, I think we have the demo working now. So rather than take another question, we'll try the demo one more time.
Malafit? Allow devices connected. אני רואה אותו מחובר פה. אתה נסה להפעיל? Still not working, but you can come see it right here.
I can tell you, I saw it on the phone. It really does work. Thank you very much. That was very interesting. Thank you.